Welcome to Hawaii, where there is science and nature all around us. Let's dive right in.
The cosmos is all that is, or ever was, or ever will be. Our contemplations of the cosmos stir us. There's a tingling in the spine, a catch in the voice, a faint sensation, as if a distant memory of falling from a great height. We know we are approaching the grandest of mysteries. The size and age of the cosmos are beyond ordinary human understanding. Lost somewhere between immensity and eternity is our tiny planetary home, the Earth. For the first time, we have the power to decide the fate of our planet and ourselves. This is a time of great danger, but our species is young and curious and brave. It shows much promise. My name is Max Dornfest, and come, let me show you my research and the research of other curious and brave physicists searching the cosmos and learning from neutrinos. Come with me, and let's dive in. In Hawaii, I've built Frost, a forest of scintillating tubes. Let's go over how it works. First, an electron antineutrino reaches the first tube. Filled with a hydrogen-rich scintillation fluid, it undergoes inverse beta decay, or IBD. In the Feynman diagram, we see that an antineutrino and a proton exchange a W boson and produce a positron and a neutron. The beauty of Frost is that directionality is distracted from the neutron as it is captured in the adjacent tube, and therefore we can calculate and reconstruct the flight. The directional reconstruction with no scattering can be calculated easily by defining a vector S sub nu as the reconstructed path. From there, it is straightforward with trigonometry using the arctan function to calculate the reconstructed angle phi.
Konnichiwa from Japan. Hi, I'm Zhihao Xu, a master student at Tohoku University. And so, our journey takes us deep into the mountains of Japan to win the opening onto the ghostly world of neutrinos. Here, in the quiet darkness, we listen for the faintest whispers from the heart of the Earth and from the farthest reaches of the cosmos. We've reached the entrance to Camland, where human engineering meets the deepest questions of the universe. Now, let's enter the heart of Camland. Moving slowly inside this enormous sphere, where every particle, every tiny flash, tells us a story about the universe and our planet.
Hey there, I'm now in California. Let's see what physics is happening here. This is my collaborator Slava. He works at Lawrence Livermore. Tell us about how the lab works with us.
Absolutely, Max. Since its founding, LNL has been a leader in high-performance computing and advanced simulations, including in neutrino physics. Here is a fun fact. Thanks to neutrinos, we actually know more about the interior of the Sun than we do about the Earth, which is right below our feet.
What's something we're working on?
One of the big questions we would like to answer is how much Earth's heat comes from radioactive decay.
So that's why neutrino detection is so important.
Absolutely. You need to have large detectors.
And about how many are passing through us right now?
There are billions and billions coming through the thumb every second. And this is a rule of thumb.
Neutrinos also come to us from much further than our sun. I'm Lila, and I study core collapse supernovae, the final stage in a massive star's life when its core collapses under its own gravity, often triggering an explosion.
Here we see material traced in blue falling onto the collapsing core, and matter, colored by electron fraction, roiling behind the translucent shockwave. Supernovae are among the most energetic events in the universe and emit around 10 to the 58 neutrinos in just a few seconds. If a supernova occurs in our galaxy, Earth-based detectors can observe its neutrinos. With a 1 kiloton scintillator detector, we may see signals such as these, with each color corresponding to different stellar masses. What can this signal tell us? First, the shape enables us to follow each stage of the supernova. This rise in the neutrino signal in the first tenth of a second indicates the outer layers of the star accreting onto the core. This decay signals that the star has entered its cooling phase. Finally, an abrupt cutoff to the signal would indicate black hole formation. In addition to the supernova stages, the amount of neutrinos seen in detectors can also help us infer properties of the initial star, like the density of its core, and can even help constrain neutrino oscillation models.